Hello, everyone. My name is Dipankar. Thank you for inviting me to say a few words on providing a perspective from Ansys, which is the company where I work, on exascale computing and its impact. First, a few words very briefly about Ansys. You may have heard of us, very widely used computational methods or applications that use computational methods throughout the industry. It's a commercial company, roughly about $1.5 billion in revenues, about 4,000 plus people in size. And the methods that are actually embodied in Ansys software cover a range of discipline areas: fluid mechanics, structural analysis, thermal, electromagnetics, semiconductor physics, and optical physics modeling. And these are all embodied into software systems that many industries use throughout the world, including simulation as part of a product development or process development process. So with this, I'd like to spend a few words describing why is it that exascale computing is going to have such a huge impact throughout industry and throughout our customer universe. An example could be seen by looking at this multiphysics simulation example encompassing structural analysis, in this case, impact analysis with LS-DYNA, which is a leading Ansys product for doing this type of simulations, and coupled with Optis, which is optical physics modeling software that models the physics of light in a completely accurate manner, including material properties, including effects of lighting, reflection, shadows, and everything. So this is not just rendering from an aesthetics perspective, but physically accurate lighting calculations going on simultaneously while we're doing the crash analysis. So this type of extremely compute-intensive calculation is not unknown for it to take days of computations, even on very large-scale machines. So with exascale computing, we expect that these very detailed, very large scale in terms of size, model size, and very difficult physics in terms of multidisciplinary physics calculations will become accessible to our customers in turnaround times that are much more useful than today. The second area is to the everyday designing engineers. And here we look at a completely different application called Ansys Discovery, which is utilizing GPU computing in a very native manner, start to finish, from graphics, geometry building, to the calculation process and post-processing itself. So because the calculation methods are highly concurrent, utilizing GPU computing in a very native manner, we're able to turn around results very rapidly in near real time. And not only that, it's done in a manner such that configuration changes like geometry can be done in process, in situ, while calculations are going on. And you can see that example, see that in action through this example, where you see the calculations responding to the geometry changes in real time. So with this, I'd like to conclude my presentation by saying that we are thrilled that the Exascale Computing Project is so strategic. It is driving innovations, driving advances on not just the hardware side, and it's not just for the few exascale machines that will be coming online in the next year or two, but also as a prime mover for advances in general HPC computing that our everyday engineer will also be able to take advantage of. It's also driving important innovations in numerical methods and algorithms that take advantage of these new architectures. This is happening in the labs, it's happening in universities, and it's happening in companies like ourselves. It's also driving the development of software tools and stacks that are so important for developers such as ourselves. So I hope you understand that our perspective is that this revolution is multifaceted, and the impact to industry is going to be huge. It's going to result in another major leap forward in the ability for simulation methods to be used as pervasively as one can imagine in every application and at every scale. Thank you for your time.